For this case, we're going to focus on production planning and profit maximization using linear programming scheduling model. So for case problem 1, Vergara Appliance Company is contemplating the production and sales of rice drying mechanism on experimental basis over the next 6 months from July to December. However, manufacturing cost and selling price vary from each month. Also, sales cannot be made in July and they don't manufacture in December. Also, there are operational limitations. The company can sell as many as 100 units per month, but since the warehouse capacity is only hold a maximum of 100 compactors, the operation is limited. And also, the company has no beginning inventory and aiming for a zero inventory at the end of their test period in December. So the goal of this is to determine how many units they're going to make and sell each month in order to maximize the firm profits. So to solve this, we're going to formulate a linear programming scheduling model. So first, we're going to copy the given in the problem, which is given table in the problem, which is the month, manufacturing cost, selling price, production, sales, ending inventory, and monthly profits, since we need to get the total profit. So for the month, we have 6 months, July to December. Manufacturing cost, we have 60, 60, 50, 60, 70, 0. Our selling price is 0, 80, 60, 70, 80, 60, 80, 60, 70, 80, and 90. So since there's still no values for production and sales because they will be our changing variable, then we'll solve the ending inventory. Then the inventory formula will be production minus the sales. Then in another row, we're going to add the first inventory to the difference of the production and sales. So we're going to drag down since it will have the same formula. Our manufacturing cost, change it to dollars. So our monthly profit the formula for monthly profit will be the selling price times the sales minus the manufacturing cost times the production. So with this, drag down since it has the same formula. So to get the total profit, this will be equal to the summation of sum of all the monthly profit. So as we can see, there's still no values for the monthly profit and the total profit because we still not do the Excel solver. So in Excel solver, we're going to click data. In data, we'll choose analyze. We're going to choose the solver. Then solver to set our objective, since the problem is we're going to maximize the profit. So total profit, we'll choose the cell in total profit, then click max since we're going to use maximization. Then our changing variable will be the production, then the sales. So the constraints are given in the problem. First is there's no sale in July. So click the cell in July and equal to 0. Then production in December is also equal to 0. The ending inventory is equal to 0 because the company is aiming 0 inventory at the end of their test period. For the warehouse capacity, less than or equal to 100 as said in the given. Sales limit will be less than or equal to 300. Then let's now move to our non-negativity, which is the production. This will be greater than or equal to 0. Then lastly, the sales also move to greater than or equal to 0. So to check the constraints, we have here. Then after putting all the constraints, we're going to select a solving method. We're going to click here, then choose simplex linear programming, then click solve. So we'll just keep solver solutions. Choose OK. Then we have here the final answer of $22,000. So in conclusion for this is the Vergara Appliance Company is can maximize their profit by strategically producing in a lower cost months. Then selling in a higher cost months, while respecting the inventory and the capacity of their warehouse.
Good day, this is Miss Lim from BSIE 4A. So today I will show you how to solve this case problem 3 using Microsoft Excel Solver. So first you have to have this select data, this option solver. So to have that, just press file, more, option, then click add-ins, then Excel add-ins go, and then check this solver add-in. Okay, so let's go back to our case problem 3. So each astronaut is given a rating from 1 to 10 for each mission based on suitability. Each astronaut can only be assigned to one mission, and each mission must have exactly one astronaut. So we have a given from astronauts from Vince to Trina, and then from January 12 to September 19. So our required is first A, who should be assigned to which flight to maximize the ratings, and B, it has now been received that Anderson is getting married in February and granted a highly coveted publicity tour of Europe for the same month. How does this affect the final schedule? So to start, we will add a sheet here, and then let's name this solver model, and then go back to rating. We will copy this, Control C, Control V here, and then let's add a row sum for the row summary here to ensure there's only one assignment per row, and then a column summary to ensure there's only one total for each summary, and here the total rating. Okay, so our decision variable is from B to K11. So a value of 1 means the astronaut is assigned to the mission and 0 is otherwise. So the objective function is, let's set our objective function here in M12. The objective function is a total rating computed using the sum product function. So equal to sum product, click this one, and then here also the solver model value, then enter. So let's delete these values, and then for our column, for this we want the sum to be equivalent to 1. So sum, drag this, close parenthesis, enter, then let's drag this to K. The same goes here, just close, enter, then drag. Then what we're going to do, go to data, solver, and then for the set objective is M12, we just press there, and for the changing value, of course it would be our B2 to K11, and then set the solving method to simplex LP and max, and let's add our constraint. So first constraint, we want this row summary to be equivalent to 1. Next, this column summary to be also equivalent to 1. For our binary restriction, we want this to be equivalent to integer. Add, and then highlight this part again, and then it should be greater than or equals to 0 or less than or equals to 1. Add, and then I think we are done. Here's our constraints, then solve. Okay, so now we have a total rating of 96, and we have ensured that there is only one for each column and for each summary. So for January 12, we have the Trina. For January 27, we have Sast. For February 5, we have Herbert. For February 26, we have Anderson. For March 26, we have Vince. For April 12, we have Fiat. For May 1, we have Moses. For June 9, we have Plain. For August 20, we have Brandon. For September 19, we have Certo. So that would be for our part A. Going back to our part B, it says here, it has now been received that Anderson is getting married in February and granted a highly coveted publicity tour of Europe for the same month. How does this affect the final schedule? So it says here, Anderson is getting married in February, and as you can see here, in our given, we have two Februarys, February 5 and February 26. So we will go back to our data, and then we will just add a constraint. Add that Anderson on February 5 is not available, is equivalent to 0. And then Anderson on February 26 is also not available, as you can see in part E. He was assigned. So let's solve. Now we have a rating of 92. As you can see, Here, Anderson is not assigned to any Februaries. After restricting Anderson from February mission, the total rating decreased to 92. This demonstrates how additional constraint reduces the optimal value in assignment problems. So I think that would be all. Thank you so much.
Yan. For this is case 5 problem. You can feel free to pause the video to read the problem. So the required in this problem is use Vogel's approximation. And A is what is the total minimum transportation cost when the company uses only 13 warehouses. Then B, which factory capacity will not be used in 100% under this optimal solution if the company operates only these 13 warehouses. Then find the best pattern of shipments, optimal solution with the lowest cost solution among the three alternative for allocation for the new warehouse number 14. Then we can see the table of the problem. So we have 7 warehouses and 7 factories and 13 warehouses since it is the problem. So how can we solve this? We can solve this using XLQM. So let's close this window, then proceed to XLQM. Then just press this QM. Then it will now open. Okay, so don't show this. So since we are dealing with transportation problems, since it is stated here, unit transportation cost, we will be using the transportation module. Okay, then fleet transportation, then new. We can write in the title unit transportation cost. Okay, since we have 7 sources or 7 factories, then 13 warehouses. Since we are dealing with optimal solution, we will choose minimize. Diba? Optimal solution. Total minimum transportation cost. So we'll be using minimization. Okay, so let's hide this panel. Okay. So first, let's change this. Let's change the label to what is the problem. So I already made a table. So we can simply copy paste this for much easier work. Then the 13 destinations or 13 warehouses. Paste. Then next is the values. Copy. Paste. Then demand and the supply. Next. Copy. Then supply. Copy. Then let's paste it. Yan. Since now we have the values and the labels, we can now proceed to the method that we will be using is Vogel's approximation method, which is that's the required in the problem, diba? And using Vogel's approximation. Okay. So using Vogel's approximation, then let's click solve. Yan. So now we have the results of the transportation. As we can see, the solution value is $350, which will be our $7,350. Our minimum transportation cost. Then which factory capacity would not be used in 100% under this optimal solution? The company only operates. So we can observe the one that is not optimally 100% used is this Saxton SK. Diba? Siya lang yung hindi na 100% nagamit. So we can simply Saxton SK. So the optimal solution shipment pattern, you can see, ito na yan. This is it. Okay. This whole answer. So that's all. Without further ado, let's proceed to the next problem. Thank you.